Have you ever really thought about what's happening when you flip a switch? Yeah, the light comes on or the heater starts to glow, but there's so much more going on beneath the surface. Electricity has these secret powers. It creates this whole hidden world of magnetism and heat all around us. So let's dive in and uncover some of that magic happening inside the wires.
Okay, so picture this. Two students, Mohini and Akarsh, are at a science fair, and they're just staring at this model crane. But get this, it's not a normal crane. Instead of a hook, it's just an iron nail wrapped up in a bunch of wire. The student, Sumana, closes a switch, and suddenly that simple nail becomes a magnet and snatches up a bunch of paper clips. She opens the circuit, and boom, they all just fall off. There wasn't a single magnet anywhere in sight, just a wire, a nail, and a battery.
So that brings us to the big question, right? How on earth is that possible? How can a plain old electric circuit, with nothing but a battery and some wire, suddenly get the powers of a magnet? That is the very first secret we are going to unravel together.
To answer that, we've got to start looking for something that we can't actually see, an invisible magnetic field. This field is the whole key, you know? It's the hidden link that connects electricity and magnetism, two things that seem like they're from completely different worlds. Let's see how it works.
All right, let's do a little experiment in our heads. Imagine you've got a regular magnetic compass, and the needle is just doing its thing, pointing north. Now let's take a copper wire, part of a circuit, and just lay it right over the compass. The switch is open, so no electricity is flowing, and nothing happens, of course. But now let's flip that switch. A current starts flowing through the wire. What do you think happens to that compass needle? It twitches. It suddenly moves away from north. It actually deflects. So think about what that means. The only thing that can push or pull a compass needle is a magnetic force. And since we don't have any other magnets lying around, that force has to be coming from the wire itself, but only when the electricity is flowing. So the moving electricity is creating its own invisible magnetic field.
And this whole phenomenon has a name, of course. It's called the magnetic effect of electric current. It's one of those fundamental rules of the universe. Anytime an electric current flows through a conductor, it generates a magnetic field in the space all around it. You stop the current, the field just vanishes.
What's just amazing is that this simple little observation was a world-changing discovery. Back in 1820, a scientist named Hans Christian Ørsted noticed this completely by accident while he was giving a lecture. Can you imagine? In that one instance, seeing that little compass needle twitch, our entire understanding of physics just shifted. He found the connection, the deep link between electricity and magnetism, two forces everyone thought were totally separate. It was incredible.
So, knowing that electricity makes a magnetic field is pretty cool. But how do we actually use that? How do we go from a wire that just nudges the compass needle to a powerful device that can lift things, just like that crane at the science fair? Well, let's figure out how to build one.
We can actually build one right now, just in our minds. First, grab a regular iron nail. Next, take some insulated wire and wrap it tightly around that nail, over and over and over again until you have a nice coil. Now you connect the two ends of the wire to a battery. The second you do that, current flows through the coil, and that nail is no longer just a nail. It's an electromagnet. Bring it close to some paper clips, and they'll leap right onto it. Disconnect the battery, the current stops, the magnetic field disappears, and the clips just drop. You've just made a magnet that you can turn on and off whenever you want.
And that is exactly what an electromagnet is. It's a coil of wire that acts like a magnet, but only when electricity is flowing through it. But as we just saw in our little build, the real secret sauce, the thing that makes it strong, is that iron nail sitting in the middle. We call that the iron core.
And this just shows you how huge of a difference that core makes. If you just have a coil of wire with nothing inside it, an air core, you'll get a magnetic field, sure, but it's going to be super weak. It might wiggle a compass needle a tiny bit, but that's about it. But the moment you slide an iron core, like our nail, inside that exact same coil, the magnetic effect gets way, way stronger. The iron basically gathers up and concentrates the magnetic field, turning a weak little force into a powerful one that can easily snatch up those paper clips.
Now, the best part about electromagnets is that you are in total control. Want to make it stronger? Easy. You can either pump more current through it by using a bigger battery, or you can just add more turns of wire to your coil. And just like any other magnet, it's got a north and a south pole. But get this, you can flip them anytime you want, just by reversing which way the current is flowing. It's an incredibly versatile tool.
Okay, so we've seen how electricity can pull off this amazing magic trick of creating an invisible magnetic force. But magnetism isn't its only secret power. There's another one, a side effect that you have definitely experienced, probably without even thinking about it.
Think back to our experiments for a second. If you were to actually build that electromagnet and hold the wires for a little while, you'd feel them getting warm, maybe even a little hot. And that is not a mistake. It's another basic property of electricity. So what's the deal? Why does a wire carrying a current heat up?
Let's imagine one last test. This time, we're using a special kind of wire called nichrome wire. We stretch it out in a circuit. Before we turn it on, we touch it, it's just room temperature, totally cool. Okay, now, we close the switch, we let the current run for, say, 30 seconds. Then we open the switch, stop the flow, and carefully just tap the wire for a split second. Whoa, it's warm. That wire got hot just from having electricity pass through it.
So what is going on here? Well, deep down at the atomic level, as electricity flows, the little electrons that make up the current are constantly bumping and crashing into the atoms of the wire. The wire is literally pushing back against the flow. We call that pushback resistance. And just like friction when you rub your hands together, this resistance creates heat. Some of that electrical energy gets converted into heat energy. This is called the heating effect of electric current, and it happens in every single circuit out there.
Now, here's the clever part. While this heat can be a waste of energy sometimes, we've figured out how to use it on purpose. Think about your toaster, your hair dryer, an electric stove, your water heater. All of those things work because we want them to get hot. They're designed with high-resistance materials specifically to generate a ton of heat. We basically turned a side effect into the main event.
So, we've seen the incredible things electricity can do. It can create magnets, it can generate heat, but this whole time, we've been relying on one key ingredient without really asking, where does the power in a simple battery actually come from in the first place? Let's get to our final section and look inside. Right, all these cool effects, the magnet, the heat, they all started with a simple, portable cell, a battery. But it's not magic, right? It's not just pulling power out of thin air. So what is going on inside that little canister that allows it to make all this stuff happen?
The answer, in a word, is chemistry. Inside every single battery, there's a carefully controlled chemical reaction going on. The very first batteries, which were called voltaic cells, were pretty basic. They just used two different kinds of metal, like plates of copper and zinc, and they were dipped in a liquid called an electrolyte, usually a weak acid. And it's the chemical reaction between those metals and that liquid that actually pushes the electrons out and creates the electrical current.
And this really shows you the key innovation. I mean, those old voltaic cells were great, they proved the concept, but they were wet, they were messy, and you definitely couldn't carry one around in your flashlight. The huge leap forward was the dry cell. Now, it's not actually dry inside. Instead of a liquid that could spill everywhere, it uses a thick, damp paste for the electrolyte. That one change made batteries portable, safe, and convenient, and it completely changed the world. And of course, things didn't stop there. We kicked off the rechargeable revolution. Now, the batteries in our phones, our laptops, our cameras, even in electric cars, they're designed so that we can reverse that chemical reaction just by plugging them into the wall. That lets us use them again and again. These rechargeable batteries are basically the power source for our entire modern mobile lives. But here's something we all know from experience. Even the best rechargeable battery doesn't last forever, does it? Every single time you charge it and then use it, the chemistry inside changes just a tiny, tiny bit. And over hundreds of those cycles, that little bit of wear and tear adds up. The battery slowly loses its ability to hold a full charge. That's exactly why your phone from 2 years ago dies so much faster than it did when it was brand new. And that leaves us with a final thought to chew on. We've gone from a twitching compass needle all the way to a planet powered by portable chemistry. It's been an absolutely incredible journey. But you know what? It's nowhere near finished. As we rely more and more on batteries for everything, scientists are in a race to invent the next big thing. Things like solid-state batteries that are safer, charge faster, and last longer. So it really makes you wonder, what will the power source of the future actually look like?